Today we're going to talk about solving systems of equations. A system of equations is two equations that are paired together. These equations, when graphed, could intersect at one point. The two equations, when graphed, could end up being two parallel lines and never intersect, or when graphed could end up being the same exact line, whereas they intersect at every single point and have an infinite number of points in common. Well, what does that mean? Well, when two equations, when graphed, intersect at one point, it means that that one point, that one xy point, is their solution. It makes both equations true. If you graph two lines and they happen to be parallel, it turns out that there is no solution. There's no point that they have in common that would make both of equations true. And when you graph two lines and they happen to be the same exact line, every point of intersection turns out to be a solution. So those lines have an infinite number of solutions. We are going to graph systems of equations today and see if they have a solution, no solution, or all solutions. We're also going to use a method called substitution to solve systems of equations, and we're going to do some practice. In real life, the reason why you might have more than one equation that you'd like to graph at a time, in real life we would use equations to help us figure out, what's the better deal of something. So maybe you're trying to decide whether or not you want to send your package via UPS or via the United States Post Office. You can figure out the total cost of your package based on its weight and the rates that each different place gives you. You can graph both of those lines and say, okay, well, which one would be the better deal for maybe a package weighing less than 5 pounds? Maybe the two lines do intersect at one point. Which would be the point saying, hey, if your package weighs 10 pounds, it ends up costing the same no matter which place you go to. Or maybe if it's over 10 pounds, the other place would be a better deal. So that's where in real life systems of equations come into play. Today we're just going to focus on the basics. So let's get down what I was just talking about. So systems of equations, basically it's where we have two equations. You could have more, but we're just starting with two. Two equations that are paired together that can either, we said, one, intersect when graphed. They intersect at one point. So maybe you have something that looks like this, two lines that intersect, and this one point here would be their solution because that x and y value make both of the equations true. So you have one solution, and it happens to be whatever that coordinate is. Or, as I said, you could have two lines graphed that are parallel. Maybe they look something like this. So they never intersect. They don't have any points in common that make both of them true at the same time. So there are no solutions. Or, when graphed, you might graph a line and then graph the second line and find, hey, it's the same exact line. Which means they intersect everywhere and therefore have an infinite number of solutions or all solutions. Let's go ahead and practice and see what this looks like. I think the trickiest part sometimes is just figuring out how to graph your lines because that's something that we've been practicing a lot. So let's just review quickly how we want to graph lines. One, you can always make a table. You could do that for every single equation. It's not always the most efficient way to work, but it does work. You choose a value for x, substitute it into the equation, and solve for y. You do that again, you have 2 points, you can graph your line. Or you can find the x and y intercepts. Substitute a 0 in for x and come up with your y intercept, or substitute a 0 in for y and come up with your x intercept. Again, you graph those 2 points, you draw your line. Or you can work with an equation in slope-intercept form. You can graph your y-intercept and then use your slope to figure out another point, and voila, graph your line. Now it's really, really important in order to figure out where these lines intersect and be accurate, we want to make sure that we are using rulers, that we are drawing our lines really neatly, because if you're off by just a little bit, your answer might be off. So you want to be neat, clear, and as accurate as possible. Let's practice by doing some of the problems on your handout. Let's go ahead and take a look at page 62, number 2. So we are given two equations. The first equation is y equals negative 2x, and the second equation is y equals x plus 3. This is a system of equations. Here's my grid, but you already have one on your page. I'm just going to note that they are counting by 2's, so I'm going to count by 2's as well, just so that we can be working with the same scale. If you look at the scales for like number 1, they count by 5's, number 3 they count by 5's, number 4 I think they count by 2's. You don't always have to count by the same thing on the x and y axis, and depending on what equations you're given, it might be better just to count by 1's or 2's or 5's. So just always make it work for you. First thing we want to do is graph these lines, and in order to do that I'm going to focus on the first equation, and that will be in purple. So y equals negative 2x. I could make a table, I could find intercepts, or I could graph this if it was in slope-intercept form. I happen to notice that this is very similar to slope-intercept form. The only piece it does not have is the plus b, because this is in fact direct variation, y equals kx. So I can write the plus 0 in if I would like and say, hey, I know that this goes through the origin, so that's the y-intercept, 0, 0. And I know that my slope is negative 2, or I can say negative 2 over 1. We need to make sure we understand how to move with a slope that's negative 2 over 1. That means I'm going to move down 2 units and to the right 1 unit. This is one way to graph this line. If instead you want to make a table and plug in 0, then 1, then 2, then 3, that is totally fine. You can do that without a problem. Let me go ahead and just graph what I have. I'm going to start with 0, 0 because that's the y-intercept, and then I get to move down 2, which would actually just be one box since that represents 2 units, and over 1. So that's kind of awkward. That's like right there. And then I'm going to go down 2 and over 1, down 2 and over 1, somewhere right there, down 2 and over 1, down 2 and over 1. So I'm just doing it many, many times because I want to make sure that my line is as accurate as possible. The more points you have, the straighter your line will be, and you'll be easily able to tell if and where an intersected point happens to be. Let's draw our line. Okay, let me see if I can adjust my line just a little bit here. Okay. Might not be as accurate for me here just because I'm not using paper and pencil. But I think this looks pretty good. Okay, so we've graphed that line. You might even want to label it, y equals negative 2x, just so you know which line is which. That's very helpful when I'm helping you work because maybe you've graphed one line correctly and one line incorrectly. We can easily see which line it is, and I can help you with that. Let's take a look at this second line. Y equals x plus 3. This one also happens to be in slope-intercept form. Again, it's a little bit tricky to tell. There is a 1 in front of this x. That's its coefficient. So the y-intercept is 0, 3, and my slope is 1 over 1. So I'm going to move up 1 and to the right 1. So 0, 3 is like right here. So I'm going to go up 1 over 1. So I'm going up half boxes. Up 1 over 1. Up 1, over 1, up 1, over 1, up 1, over 1. Okay, up 1, over 1, up 1, over 1. Or you know what? It's the same thing as up 2 over 2. So I could just do that, and then I can move up by whole boxes. So up 1, over 1, up 1, over 1. Let me go ahead and graph this line as well. Okay, again, it looks something like that. It's hard for me to line it up perfectly. 0, 3, something to that effect. Okay, and I will say that all of the intersected points that you get will be whole numbers. So if your lines are a little bit off and it looks like one is in, 2.5 and the other one's like 3.5, just do your best to figure out which whole numbers they are or integers they are closest to if they happen to be negative. And in this case, let's see, if I was to look, this looks to be about -1 comma 2. Their intersected point looks like it happens to be -1 comma 2. So again, it is tricky to get them perfectly lined up. That's why you want to use a ruler. We can check this. I can say that these intersect and that the solution is -1, 2, because whenever I substitute a -1 in for the x value, I should get 2. And let's just check it. Well, -1 times -2 is 2, and -1 plus 3 also happens to be 2. So it checks. Let's go ahead now and take a look at a situation where we would use something called substitution to figure out a solution to a system of equations. Substitution involves no graphing. So solving systems of equations using substitution. This is more just manipulation of our equations, substituting, solving, and it works out really nicely. We're not going to use the same types of equations that I just gave you. We're going to start off with more basic equations, so it should be pretty easy to work with in terms of the numbers. So let's say I gave you a system of equations like this. You have y equals x minus 8 and y equals 1. This equation is in slope-intercept form. If we wanted to graph it, it would be we could start this at -8 on the y-axis and then go up 1 over 1, up 1 over 1. We'd get a diagonal line. This equation is special. If you remember, this represents a horizontal line. So if these were to be graphed, it would look something like this. So I know that these do intersect, but again, I don't have to graph it to figure out the solution. So what can I do? Well, if I know that y happens to equal 1, I can substitute y equals 1 into the first equation of y equals x minus 8. Because if I know that y is always equal to 1 with this second equation, I want to know, well, in the first equation, what does x equal when y is 1? So let's go ahead and substitute. 1 equals x plus -8. I just changed it to plus negative to make it a little bit easier to look at. I am going to solve by adding 8 to each side, and I find that x equals 9. This is not the final answer. Remember, your solution always has to be an x, y coordinate. I want to know what coordinate makes both of these equations true. So it turns out that when y equals 1, x equals 9, and this is the solution to both equations. It makes both of them true. If I put in 9 up here, 9 minus 8 is 1, and with the second equation, it doesn't matter what your x value is, y is always going to equal 1. So this is where they intersect. We can take a look at another type of example. Let's say we have 26 equals y plus x, and then y equals x. This one's a little bit trickier because we're not actually given a value for y. We're just saying y and x are the same thing. When you graph this type of equation, you'd get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. It would be a diagonal line. The other equation, we'd get some kind of line as well, but again, we don't have to graph it. If I know that y equals x, I can substitute x in for y, or vice versa, and get x plus x. Let's combine like terms. We get 2x. Let's divide by 2, and I get x equals 13. But like I said before, that's not the only answer. The final answer, I should say. What does y equal? Well, when x is 13, y has to be 13. So our solution is 13, 13. We will practice this a lot in class tomorrow. I'll see you then. Thanks. Bye.